In this work, we consider the problem of approximating the spectrum of a graph. What is the spectrum of a graph? Given an undirected graph G with n nodes, you can represent it by a matrix. It turns out that for many settings, the right matrix is not the adjacency matrix, but the normalized Laplacian. And the spectrum is defined to be the vector of sorted eigenvalues of this matrix. Why might you be interested in computing the spectrum? These eigenvalues contain lots of structure information about the graph, such as the extent to which it has commutative structure or can be clustered at different scales. So how quickly can the spectrum be computed or approximated? It is well known that it takes matrix multiplication time, number of nodes to the 2.37, to compute the spectrum exactly. Can we make it faster? Our main result is the following. Given access to a data structure that lets you select a uniformly random node from the graph, and that lets you select a uniformly random neighbor of any specified node, we give an algorithm that approximates the spectrum, and the total runtime of the algorithm and the number of queries to this data structure that the algorithm makes are independent of the graph size, and depend only on the desired accuracy of the approximation. How is this possible given that the spectrum is a list of unsorted numbers? Well, our algorithm will output a list of quantiles of this spectrum. So if the graph has a million nodes, we might output an approximation of the 1000th smallest eigenvalue, an approximation of the 2000th smallest, 3000th smallest, etc. So does it work in practice? Here we illustrate the result of running our algorithm on a number of real-world networks. The blue circles in the plot show the approximated spectrum returned by our algorithm. The red plots depict the ground truth, and it was computationally prohibitive to compute the exact spectrum for the larger graphs. Beyond illustrating that our algorithm works well, these plots also illustrate some of the structure inside that the spectrum reveals. For example, all the row networks, which are the top left plots, have a very distinctive linear structure. This structure would not be apparent from only looking at the second smallest eigenvalue, or the smallest several eigenvalues. There are also some nice structural properties that can be read off from the spectra of the other networks, such as the anti-symmetry of the social networks, which is not found in the collaboration networks. Thanks for watching, and we hope to see you at KDD.